So we've been talking electric flux, meaning the flow of electric field through a surface. The fundamental equation, remember, is the integral of the electric field dotted with the area vector. We do need to integrate if the electric field is not uniform over the surface, or as it passes through the surface, I should say. We're going to talk about electric flux through a closed surface. So far we've talked about an open surface, meaning the flux. So if we have an electric field, the flux through something like a rectangle or a circle or a triangle. These are considered open surfaces because they're simply a plane. A closed surface is something like a sphere, I'm trying to draw a sphere. So a closed surface would be something like a sphere, a cylinder, a box, anything that has an inside and an outside. So the inside is closed off from the outside. On our integral, we write this with a circle around the integral sign. That represents that it is a closed surface. But we're going to find that this equation can, in some situations, simplify nicely. So I want to walk through that for just a second. So for example, if I have a point charge, we already know the electric field due to a point charge points radially outwards in all directions. It gets weaker the farther away from the point charge. And so I want to talk about the electric flux through some sort of closed surface that I'm going to choose. I'm going to choose a closed surface, but I want to choose a surface where this integral will simplify, meaning is there some sort of closed surface I can choose where the electric field would be uniform? Meaning, is there some type of surface I can draw that the electric field, as it passes through that surface, will be the same value everywhere? Well, we know that yes, the electric field for a point charge depends upon the charge itself. It depends upon how far away from the charge, and then we have our constants. I've been writing that as a capital Q, so let me put that back in. So that capital Q represents this point charge. I know the electric field will be the same value, the same distance from the point charge. So as long as this distance r is the same, this electric field is going to be uniform. Now we do need to imagine this as a sphere because I want this to be a closed surface. Three-dimensional drawing is not my forte, but we'll try. So I have chosen a surface to talk about the electric flux through, and the surface I've drawn is such that this electric field is uniform, which means I can say the electric flux through this sphere. So the flux through this sphere I've drawn. This sphere is just something made up by me. It's an imaginary closed surface. But because because I know the electric field has the same value as it passes through that sphere, because I've chosen to put the point charge at the center, the integral is no longer there, right? Integral of dA is the area vector. So we have the electric field dotted with the area. Now the dot product. We already know the electric field is pointing radially outwards. The area vector for a closed surface always points normal to the surface, and it specifically points outwards. So at any point on this sphere I've drawn, I can draw the area vector normal to the surface and pointing outwards. That makes that radially outwards as well, which means E and A in this specific situation are parallel to each other. Meaning we're taking the electric field value times the area value. So if you recall, the nature of the dot product is to multiply the components of the vectors that are parallel to each other. And so in this specific situation, where I have chosen this sphere so that the electric field has the same value as it passes through the surface, and it naturally happens that the electric field vector and the area vector are parallel to each other, the electric flux through this sphere, this closed surface, simplifies in this specific case to be simply the electric field times the area. So the electric field value we already know, because we know the electric field due to a point charge. The value of the electric field as it passes through this spherical surface I've chosen is our constant K, or 1 over 4 pi epsilon naught, times the value of that charge in there divided by r squared, the distance from the center. A means the surface area that the electric field lines are passing through. Well, I chose a sphere for a specific reason. The surface area of a sphere is 4 pi r squared. So E times A, this is giving us the electric flux through this spherical surface. The 4, the pi, the r squares are all canceling. And this is telling me that the electric flux through this spherical surface I've chosen is equal to the value of the point charge divided by this constant, epsilon naught. This simplifies very nicely, very easily. And interestingly, it turns out that any time we are calculating the electric flux through any closed surface at all, this electric flux will always equal the charge that is located inside the surface divided by epsilon naught. Now, it does not mean that this integral will simplify nicely every time, but the flux itself will always be equal to charge located within that surface divided by the constant epsilon naught. This is called Gauss's law. Gauss's law is calculating for electric flux through a closed surface. Now, it should hopefully make sense. Coming back to my picture, let's see, I drew 7 electric field lines is how I drew the electric field around this point charge. All 7 of those electric field lines are passing through that spherical surface that I chose to draw. Now again, I chose the spherical surface so that the electric field would be uniform. It would have the same value as it passed through the surface. But imagine here for a second. Let me choose another color. If I had chosen to draw, say, a cylindrical surface, still such that that charge was located inside the cylindrical surface. Now, the electric field, of course, would not be uniform as it passed through the surface. Points closer to the charge would have a stronger electric field. Points farther away would have a weaker electric field. But if you recall, electric flux, if we have a pictorial representation of our surface and the electric field, we can simply count the number of lines passing through. If we're talking about the electric field flowing through the surface, we can totally count those lines. And with this cylindrical surface, all 7 of those electric field lines will pass through that cylindrical surface. Therefore, the electric flux through the cylinder would be the charge that's in there, that point charge Q over epsilon naught. Now, it would not be equal to simply E times A. And that's because the electric field is uniform, the electric field vectors and area vectors are not parallel. But it would most definitely equal the charge enclosed divided by epsilon naught, which is actually pretty awesome because that simplifies finding flux. If we can find the net charge located within the closed surface, then we can find the flux. We do in some situations, it's limited, but in some situations we can work backwards from knowing how much charge is located within the closed surface and work backwards to find the value of the electric field, which I'll show that in a separate video. But here, Gauss's law, the electric flux through a closed surface, some sort of three-dimensional surface, like a sphere, a box, a cylinder, that electric flux ends up being equal to the charge located within the surface divided by epsilon naught.